Lesson number 5 is our final lesson in the geometric vectors introduction. And today we're looking to apply those vectors specifically in the context of velocity. So our learning goals are the same as lesson 4. So just as you saw with force, we're going to use the phrase resultant velocity. So this is often referred to as relative velocity, especially if you've taken physics. And this is the result of when two different velocities act on an object. And they depend on what you're considering the velocity being relative to. So one of the common examples would be a plane. So a plane is capable of an air velocity. So that's the velocity relative to the air. And it's what the plane is capable of in still air. And is also pushed by a wind. So there would be velocity now because of the wind, which is relative to the ground. These two velocities combine to form the resultant velocity. In this case, the velocity relative to the ground, which we call the ground velocity. So as a brief little example, we could say that a plane is traveling with an air velocity heading northeast. And there is a easterly wind affecting this. And you can see in my little note there, I've said that winds are usually described as the direction they come from. So when I say easterly wind, let's just have a quick reminder of a little compass rose here. It's north and east are those two directions. So hence the plane's air velocity is northeast. And we're going to have an easterly wind. So that means the wind is coming from the east and actually heading west. So there'd be this easterly wind. And that, of course, is also a vector. So our resultant would be your actual air velocity is actually that way. So it's still relatively northeast in terms of the actual direction that the plane would travel in, but would be slightly more to the north. So we would have to have magnitudes here, and we could calculate the actual bearing that the plane has, and we could figure out what its actual speed is as well. So I found in the previous lesson that doing two examples got to be a little too long. So I used the previous screen to kind of give you one of the common examples for velocity. And this is the next most common one. So we're going to focus in on this example here to help you through your work. So we have a river that's 2 kilometers wide. So here's perhaps the banks of my river, and I know that this river is 2 kilometers wide, and it flows at 8 kilometers per hour. So we also need to know where up and downstream are. Because current will flow downstream. So Anna is driving a motorboat which has a speed of 20 kilometers an hour in still water. So that would be her velocity relative to the water. And she heads out from one bank in a direction perpendicular to the current. We've already kind of figured out that your current is going to flow that way. A marina lies directly across the river from the starting point on the opposite bank. So we know that she is going to head out from a particular spot on the bank, perpendicular to that. And we also know that there's a marina over here. And that there's a current that's going to push the boat downstream. So she's going to have that water speed of 20 kilometers an hour. And there's an 8 kilometer per hour current pushing her down. So how far downstream will the current push the boat, and how long does it take to get there? Because we can see that if those are going to be the two velocities we're dealing with, that her boat will actually end up doing something like that. So your resultant vector will head on an angle. So in order to figure out how long it will take and how far downstream, we do need to actually figure out some things here. For instance, we know that she's going to do the perpendicular thing at 20 kilometers an hour, and we know that it's 2 kilometers in length. So we also then know that the triangle formed will be similar in terms of distance. So if it's 20 kilometers an hour and 8 kilometers per hour, then the 2 kilometer diagram also needs to have the same angles and be in the same ratios. So for our distance, we know that it's going to go over 2, and then she'll come down a certain distance. And so to get from 20 kilometers an hour to 2 kilometers, notice that we could divide by 10. And that would get us to that value. So we're also going to take 8 and divide that by 10. So this would be 2 kilometers. And then 8 divided by 10 is 0.8 kilometers. So there we know how far down the river she'll end up. So the current will push the boat 0.8 kilometers downstream. And how long it will take to get there. This is part A. We got this as 8 divided by 10. And it was because the 20 divided by 10 got us to the 2 that we already needed. And so for the time, well, we know that speed is distance over time. So that means that time is distance divided by speed. So distance is 2 kilometers, and the speed is 20 kilometers per hour. So that will be 0.1 hours. So it will take 0.1 of an hour for her to go across. And of course, we can convert that to minutes. And 0.1 times 60 minutes would be 6 minutes. So therefore, we'll end up with 0.8 kilometers. Downstream. Okay, let's take a look at part B. If Anna decides she wants to end up at the marina directly, in what direction should she actually head out so that the resultant velocity will allow her to end up at the marina? And what will that resultant velocity be? So what we know here is that she needs to end up with her resultant velocity going directly across. We know that there is going to be the current pushing her. So she's going to get pushed down by that current, which means that she needs to take a heading that will allow us to form the triangle to create this resultant velocity that we actually need. So we've got our current, 8 kilometers per hour. We know that's going to go directly down. We know that her boat speed is 20 kilometers per hour. And this is going to form some angle. We need to figure out what that angle is going to be. But as you can see, we do know this will form a right triangle. So that's actually pretty helpful. It means that we can use primary trigonometric ratios to come up with our angle. So we notice that we're dealing with something that's opposite to our angle and the hypotenuse, so we should be using our sine ratio. And we'll pull out our calculator to figure out what that's going to be. And we get that this will be approximately 24 degrees. So we can conclude now that her heading should be 24 degrees extreme. And now we want to know what the actual magnitude is of our resultant vector. That's the second part of our question, right, is what will the resultant velocity of her boat be? And so we need to find the value for the resultant vector, the red vector in that diagram. And you can see again it's a right triangle, so actually Pythagorean theorem will work nicely for this. So 20 squared will be 8 squared plus the magnitude of resultant squared, which means the magnitude of this guy will be 400 minus 64 square rooted, which will give approximately